Hi there, and welcome to Lecture 2 for Biostatistics. Today we're going to be looking at basically these four things. So we're going to be looking at what are the assumptions of the linear model. We're going to be looking at what happens when we add, if we have more covariates that we wish to add, and how do we test these things with a particular test called the F-test. And then we'll be looking at models with factor variables. So if we've got categorical data, can we also include those in a linear model? And of course you can. So recall that the linear model is basically looking at estimating the average of the response variable measure for particular values of the explanatory variable. So for example, we're looking to estimate the average weight of a donkey, given that we know what their heart girth is, right? So for each heart girth, what would we expect the average weight to be? And we assume that that relationship takes a particular form, which is a straight line relationship, right? Where you've got a an intercept and then a slope associated with that variable. And we fit that model by finding our best guess at what alpha and beta are based on some mathematics criteria, which essentially is minimizing the variation in the residuals, the leftovers after we fit the straight line. So essentially we're minimizing the distance between each observation and where we think the observation would be if they were perfectly predicted from the straight line model. And then we have some assumptions that we note about those residuals, and if the residuals satisfy those assumptions, then we can say even more about the alpha and beta. Particularly we can categorize the uncertainty associated with them, and we can test, for example, whether beta is 0 or not. Beta 0, of course, would mean that the average of y is just equal to alpha, right? If beta 0, then that term goes away, in which case x does not affect what the average of y is, right? And that those assumptions essentially allow us to go from the sample that we have through to the population. So you remember we have four assumptions that follow this acronym mnemonic line. So the linearity, which is the most important one, which is basically that we get the form of the equation correct, so that the leftovers, the scatter of the observations around the line, no longer depend on x. Then we have independence, which is that the residuals aren't dependent on each other, so you don't have any clustering of observations or any autocorrelation in time, where you repeatedly measure the same individual over time or anything like that. Normality, this is the least important because we've got the central limit theorem, but we do make an assumption that the residuals are distributed normally, and of course usually that assumption will be broken, but generally it doesn't matter. As long as your sample size is large, then whether the residuals are normal or not doesn't actually affect the distribution of the estimates of the alpha and the beta. Okay, so just like whether the distribution of a sample was normal or not didn't affect how we computed a confidence interval, right? The confidence interval, the distribution of the sample mean is going to be normally distributed even if the data are not, as long as the sample size is large enough. And the last one is equal variation. So we assume that the residuals have constant variation that doesn't depend on x. So as you change your x, as you move across the plot from left to right, the amount of scatter around the line is relatively constant. And we check these things by using diagnostic plots, right? So you remember there's essentially four diagnostic plots that are produced, and with those we can assess linearity, normality, and equal variance, but we can't assess independence. And the reason is that the lack of independence usually comes about due to how the data are collected, and we'd need the information about how the data were collected to assess that. And often we may not have that in the final data set. And the last thing that we can also look at is whether there's outliers in the data that have undue influence on our model fit. So you remember that if you have an observation that's very extreme in terms of its x value, then it's going to have quite a large leverage on the final model, and also if it has a very extreme residual, it will also have. So that's an extreme y value given its x. it'll also have a large influence on the model, and a combination of both of those things at once is kind of what you want to avoid. And we get these diagnostic plots just by running plot on the model, okay? So with our donkey data, remember we had heart girth on the x-axis and body weight on the y. Then when we do the model diagnostics, we get these 4 plots. You remember that the first one here, the residuals versus fitted, the first plot, that's the one that we assess both linearity and equivariance. So to assess linearity, what you're looking for is presence of a trend, right? So you can see here, trying to ignore the red line, you can see that the most of the residuals are positive on the left-hand side, and then you get a few more that are negative on this side as you go through the middle, and then as you get through the larger numbers, again, the residuals tend to be positive. So there's a curvature present there, right, in the average. So that suggests that we're not getting the form of the relationship correct. We're assuming a straight line relationship when perhaps it should really be a little bit curved. And the other thing we're assessing is the scatter around the trend. So given that the trend is curved, how much scatter is there around the trend, and is that scatter constant as you go from left to right? And in this case, we get a small amount of scatter on this end, and that increases as we go, and we get more and more scatter as we go across. So there's kind of fanning out of the residuals. So in this case, probably linearity and equivariance do not hold. And we get that just from that one graph there. Normality we assess with the normal QQ plot. Essentially what you're looking for is most of the observations along the straight line here, which these ones are, and you expect it to drop off at either end, okay, in either direction really. Usually, unless you kind of get a massive curvature present in this plot, we don't worry about it. We can just ignore this one down here, the third plot, because this is just a rescaling of this one, okay? So we can kind of cross that one out. And this last one is not assessing an assumption, rather it's assessing whether you have points with high influence. And what you're really looking for is, see these dashed lines up here, these are the Cook's distance lines. What you're looking for is, are any points past those lines, so up in the top right or bottom right of the plot. And if there are observations past those points, then that suggests that those points have high influence, so your model result, the values that you've got for your intercept and your slope and so on, are being greatly influenced by that one observation. So it pays to kind of take that observation out, refit, and make sure that your conclusion is similar. Okay, so this was the problem with the residuals versus fitted values for the donkey. We don't have linearity, and equal variation also doesn't hold. And you can kind of see it, now that you know that it's there, you can kind of see it in the original data. So you can see that it's kind of a, if you put a trend through here, it's going to be a little bit flatter in this section and then get steeper as we go. So it's going to be a slight curve, right? And we can fix that with a log transformation. So transforming the heart girth and the body weight with a log transformation makes that the curvature that we saw present there, it kind of flattens it out, and now it's nice and straight. And when it's straight, you can then fit a straight line. And this is the usual tool we use to deal with lack of curvature, or rather curvature, lack of straightness, I suppose, is that we basically hit it with a hammer until it's kind of in the shape that we can deal with, and then we go ahead from there. Okay, so this is what the residuals versus fitted plot looks like for the log-log model. So you can see here we're fitting a log transformation of body weight and heart girth. And you can see that nice and flat here, no trend, and also fairly constant variation as we move from left to right. Okay, so this is much better. So what we've actually done is we've transformed the data and then fit a straight line, which is equivalent to fitting a curve on the original data, a power curve. And so one way to visualize that is to use the visreg package, which you'll do in the lab 2. And essentially what we're doing is if we plot the data on a log scale, then what we're doing is we're fitting a straight line. And you can see that the straight line fits really well. You can see, as per usual, there's a little bit of uncertainty at each end, right, which is the grey band. That's the confidence interval for the line, so that's potentially where the line might be. There's less uncertainty in the middle, of course, because the line is very rigidly fixed there. We've got lots of data there holding it in place. And if you look at that same model, so if you transform that model back to the original coordinates, so the original heart girth scale and body weight scale, then you can see that we've actually fit a curve there. So that's what our model looks like on the original space. Okay, so generally that's how we go about dealing with lack of linearity, is we do a transformation, typically a log transform of either y or x or both, and we then assess the model there using just a normal straight line relationship, and then we can kind of undo the log transform to go back, and we get some sort of a power curve like this one here. Okay, so in summary, when you're assessing the model assumptions in a linear model, you fit your model, and then you first look at your residuals versus fitted plot, so the first diagnostic plot. If you see curvature on that, or increasing scatter from left to right, a log transformation is often the solution. So try doing a log transform and then refit. And only once you've kind of got that right, so you've taken care of the lack of linearity, and you've got a nice, fairly straight line and fairly constant scatter, then you look at the residuals versus leverage plot in order to just check you don't have influential outliers. You don't really have to care about the other two plots as long as you have plenty of data. So as long as you've got kind of a couple of hundred data points, then the normal QQ plot is probably going to be fine anyway. And even if it's not, it's probably going to be okay. And then the third plot, of course, is just a transformation of the residual versus fitted plot, so you don't have to care about that one. Okay, if you do find that you've got influential outliers, then the best thing to do is just remove those outliers, refit the same model, and assess for a change. If you don't get much of a change, then it doesn't really matter, right? Your results are robust to whether those influential outliers are included or not. If you do get a change, then you've got a decision to make, right? Are those influential outliers real? And if they are, then perhaps they should be included, and my results should be reported as such. But I think you probably want to include kind of like a sensitivity analysis where you say, well, if I didn't have these observations, then my answer would change a little bit, and here are the implications of that. Okay, so that's the linear model with just one variable, right? So we've got the outcome variable, body weight, explained by just one explanatory variable, heart girth. But of course, there's relationships between body weight and the other measures as well, right? So while the strongest relationship was with heart girth, because the scatter was was tightly clustered around the trend line, we also have information from the umbilical girth, the length, and the height that we should really be using as well, right? Why use just one when we've got 4 measures? We might as well use all 4. Okay, the advantage of using more is that we're likely to explain more of the variation in body weight. And if we explain more of the variation in body weight, then that means that the unexplained variation is smaller, and therefore our predictions will be more precise, right? We'll have smaller confidence in prediction intervals, and thus, a more useful result. And it's really not going to be much more complicated, right? If you are out in the field measuring a donkey, whether you just measure just the heart girth or whether you measure the heart girth, the length, and the height, probably isn't going to take much longer. And if you can get you can get a better answer from having the 3, then you might as well go ahead and do it. And as far as the kind of the underlying theory goes, really it's just adding another term to the linear model equation. So before we just had the mean of y is equal to some constant, some intercept alpha, plus some slope times the heart girth, and now we just got another slope times another variable, perhaps the umbilical girth, plus another slope times the height, plus another slope times the length, and so on. Okay, the actual underlying maths works basically the same way. We just minimize the residual sum of squares of the essentially the variation of the residuals, and that then defines what the best values of their alpha, beta 1, beta 2, and so on are. And then our model assumptions are all on the residuals. They're not on the x values or the y values. They're on the residuals, and so the same model assumptions work in exactly the same way. Okay, so the complexity of the model doesn't actually change how we assess whether the model assumptions hold or not. We assess them the exact same way. We plot you produce the diagnostic plots and then check for linearity and so on. What we do get, of course, is we get estimates for each of the variables that we put in the model, so we get extra lines in the summary of our output. So if you want to know about the underlying maths, basically you can rewrite the linear model as a matrix equation, And when you do so, once it's in a matrix form, adding variables is just adding more columns to what's called the design matrix, the X, and therefore adding more values to the vector of coefficients beta. But once it's set up in a matrix equation, essentially the maths then follows exactly the same way as it does for the one variable case. I include that just so that, if you have a look on Wikipedia or whatever, you'll probably get linear regression expressed in this way. So it's just so that you're familiar with that. Right. So with the donkey data, if we just had body weight in terms of heart girth, then we get this here. So the formula here is minus 195 plus 2.83 times heart girth. Okay. If we were to go in and add an additional variable, so here we're adding in the umbilical girth as well, then you can see we get an additional line for the umbilical girth down here. Okay, and you'll also note that the heart girth coefficient here has changed. So before it was 2.83, and now it is 2.39, right? So your estimate for the effective heart girth changes when you add other variables in. And the reason that it changes is because what these actually represent is a 1 unit change in heart girth with everything else staying the same. So assume you had two donkeys with the exact same umbilical girth, but their heart girths differed, right? One of them was, say, 2 centimeters, had 2 centimeters more heart girth than the other, right? So the umbilical girth is the same, but their heart girths differ by 2 centimeters. Then their body weights are going to differ, according to this equation, by about 2 lots of 2.4, right? So about 4.8 or something kilos, right? Now that's a different answer to what we got before. We would be saying if the heart girth differed by 2 centimeters, then the weight would differ by 5.6 kilos. And the reason is that you're unlikely to get two donkeys where the heart girth changes but the umbilical girth doesn't, right? The two measures, heart girth and umbilical girth, are correlated. When one of them goes up, the other one tends to go up as well, right? As the donkey gets bigger, both of the girths tend to get bigger, right? And you can see that if you combine those two numbers together, the 2.39 it is and the 0.42, you get about, just over 2.8, which is what we had before. So it kind of makes sense, right, that those two things are related. Now you can see the p-values here, okay, for heart girth is still really, really tiny. So that's telling us that heart girth does make a difference. And similarly, the p-value for umbilical girth is really tiny. So that's telling us that umbilical girth also makes a difference. You can see that the R squared is a little bit higher. So before it was 0.80 and now it is 0.82. So we've explained more of the variation by adding the umbilical girth in. Okay. Now the key thing that we need to be careful of here is what the definition of this p-value is, right? Because the p-value here isn't answering the question, is umbilical girth important? Rather, it's asking the specific question, is umbilical girth important after controlling for heart girth, right? So after taking heart girth into account. And similarly, the p-value for heart girth is saying, is the heart girth important after accounting for umbilical girth, right? So this p-value for heart girth here is going to be different to what it was before. Okay, the numbers here are the same because they're so tiny, but they'll actually be a little bit different because we've adjusted for umbilical girth in the second model. Okay, so we don't want to answer the question which variables are important. Rather, we want to say which variables are important after accounting for the other ones. And that allows us to then answer questions like, should I bother including the umbilical girth, measuring my umbilical girth, as well as the heart girth, or does the heart girth itself, just good enough? Then this model was telling us that actually you should bother measuring umbilical girth because it does tell you something. Okay, admittedly it doesn't tell you all that much, but it increases our overall R squared by 2%, which means that the leftover variation has gone from 20% down to 18%. So we've improved it by about 10% or so, right? 20% down to 18%. So we haven't done too badly. Okay, so which of the variables are important after accounting for the other variables is exactly the same as saying which of the betas are non-zero. So what we're saying is, could this coefficient of umbilical girth here be 0? And the p-value is saying not very likely, right? So when we look at the estimate for umbilical girth and its standard error, right, you'd expect 95% of the time for the umbilical girth to be within the range 0.42 plus or minus twice 0.07. So that's 0.42 plus or minus 0.14, which is 0.28 up to 0.56, right? Both of those numbers don't include 0, and similarly the p-value then is really tiny, right? So we'd be concluding that umbilical girth does in fact tell us something. What about when we add more things in, right? So here we've got a model with heart girth, umbilical girth, length, and height, right? Then we just get extra rows in the summary output, and again the coefficient of heart girth has changed a little bit. The coefficient of umbilical girth has again changed a little bit, and we've got length and height, and that's just because all these things are correlated, right? And when you're assessing this, you can see that heart girth is important because its p-value is small after accounting for the other three. Similarly, umbilical girth is important because its p-value is small after accounting for the other three. Length is important after accounting for the other three, but height is not. Right? The p-value for height is 0.06, which suggests that you could get an estimate of height, of the order of 0.25, about 6% of the time, 6.5% of the time, just through to chance. Right? So this is suggesting that that height doesn't really tell us much over and above the other three. Okay. Note the multiple R squared is increased now to 85%. Right, so there's only less than 15% left over now, variation. Okay, so heart girth, umbilical girth, and length are all important after accounting for the other stuff. Height is not important after accounting for the other covariates. But that does not mean that height is not important, right? Clearly, it just makes common sense that height would be important for weight, right? Taller people are going to be heavier. Taller donkeys are going to be heavier. And of course, we can show this with a linear model. We could have, looked back at the graph of body weight versus height. Height would tell us the same thing, right? But if we fit height in our linear model, then of course we get a tiny p-value, right? There's a lot of evidence that height is useful for explaining body weight. It's important to explain body weight. It explains 61% of the body weight. But the key thing we found is that it's not important if you already have measured the other three and included those in your model. Okay? So that's the key difference. So the overall thing is that if you've measured the heart girth, the umbilical girth, and length, then it doesn't really give you much, measuring the height won't give you much more information over and above those three. So if you're going to go out and measure some stuff, don't bother measuring the height, just measure the other three. That'll be enough. Okay? And of course, we've explained now 85.2% of the variation. Now, of course, like in our other models, we have this overall p-value down here. Now, you remember that the overall p-value meant, does anything in my model explain the body weight? And when we just had the one thing in the model, it was the same, right? So the p-value was the same as the p-value for heart girth if we only have heart girth in the model, right? Because there's only one thing. The p-value, overall p-value is saying, it does anything explain it? We only have one thing there, therefore it's the same as saying, does heart girth explain body weight? Now we've got a bunch of things, so it's saying something different. Instead it's saying, is any of the three things important, or the four things here important? And of course they're individually important, so the overall one will of course be important. But the test it's using is different. Okay, so we're going to have a look at what this F statistic here is talking about, because it'll be valuable later. Okay, so that's using a distribution called the F distribution, and so it's an F test. So really, before we look at the coefficient table, we should be looking at the overall p-value just to see whether the model is any use at all, right? If the overall p-value is large, then that's saying that nothing in my model is much use to you, so there's no point even bothering looking at the coefficients table, right, to find out if any of the things in the model are important, or even to write down the formula or anything like that. We don't care at that point because nothing in the model is useful. So the hypothesis under test are any of the betas non-zero, right? So are any of the coefficients non-zero? If they're all zero, or if they all could be zero, they're not different enough from zero to care about, then that's saying that the mean of y is not related to any of the x's, and so our model was useless for predicting the body weight, right? And we can answer that question, we can test that hypothesis by comparing the variation in the residuals to the total variation in y. So essentially all we do is we say, is the variation in the residuals less than the variation that we started with, right? We'd expect it to be less if our model was doing anything. If our model's not doing anything, then the residuals will have the variation equal to the original y. And essentially, so what we do is we look at this ratio of variation explained to variation unexplained. It's kind of related to R squared. You remember R squared was variation explained divided by total variation. This is a little bit different in that it's variation explained divided by variation unexplained. Okay, and there's another formula in terms of the various variances that you can compute. Okay, so we look at that ratio, and the process that we're going through here is then called analysis of variance because it's looking at that ratio of variation. And you can see here that on the top we have variation explained by the model, right? So, so if your model explains lots of stuff, that will be a large number, right? And on the bottom we have variation unexplained by the model. So if your model explains lots of stuff, then you're going to have a large number on top and a small number on the bottom, right? You're explaining most of the variation in the response. So there's very little variation left over, and so you get a large number divided by a little number, which is a big number. All right. So F is big if your model is good. If your model is useless, then you're not explaining anything. Everything is then unexplained, so you get a large number on the bottom and 0 on the top, and so F is 0. Right? So the magnitude of F tells you how good your model is. So we'd expect F to be close to 0 if we're not explaining anything. We'd expect F to be large if we're explaining lots. Right? And so that's so under the hypothesis that the model doesn't explain anything, i.e. all the betas are 0, we'd expect F to be 0. Otherwise, we'd expect F to be non-zero, some large positive number. And there's, of course, a distribution that defines how large we'd expect F to be with various amounts of confidence, right? Just like there's a normal distribution that explains, how far away from the mean you'd expect to be for given levels of confidence, right? It's the same basic idea. Okay, so this overall F statistic here, this is the value of F, 550, near enough. There's some parameters associated with it, the 4 and the 380, which basically have to do with the amount of data you have and the number of parameters in the model. So the 4 is the number of parameters in the model, and the 380 is the total data size minus the number of parameters in the model minus 1. You don't have to know any of that. And then there's a bunch of maths that links these three numbers together and gives you the p-value, right? So all we have to look for is the p-value, and we see the p-value is super tiny, right? So our conclusion would be that the relationship that we see from the model in our sample is super unlikely to have arisen by chance. Therefore, something in our model is describing body weight, okay? Which in this case isn't it's common sense, right? But there we go. Now the advantage with the F test is that it now allows us to know how to test whether categorical variables are also important. Okay, so remember that the linear model equation is describing the average of the outcome variable given the value of the covariates, right? So for a continuous variable like heart girth, you're using a straight line relationship for that, right? So you're allowing the body weight to increase or decrease at a constant rate as you vary the heart girth. With a factor or categorical variable, instead the values of that are just which group you're in, but we'd still be, with a linear model, we'd still be modelling the average. So what we'd be doing is modelling the average in each group. Okay, so the linear model would estimate the mean in each group. to actually put it into a model where we can write down an equation, we need to be able to convert the categorical variables into numeric variables in some way, and we do that through indicator variables. Okay, so the simplest case is where your categorical variable just has two groups. Okay, if you've got two groups, then what we do is we introduce an indicator variable z, which is 0 if you're in the first group, and 1 if you're in the second group. Right, so z is a 0, 1, kind of a switch, and then the equation is just the mean of y is equal to alpha plus beta times z. Similar form to what we had before, but now we indicate that. But now we know that z only takes two possible values, 0 and 1, and that's it. Okay. So because z takes just two values, we can actually write down all the possibilities for what the mean of y is. Right. So z is either 0 or 1. So if it's 0, then beta times 0 is 0, and we just get the mean of y equal to alpha. So that's what, so the average in level 1 in the first group is going to be given by alpha. In the second group, z is 1, and so if you put z equals 1 into that equation, you get alpha plus beta times 1. Beta times 1 is just beta, so you get alpha plus beta. So the average in the second group is alpha plus beta, right? So that means that beta represents the difference between the first group and the second. So alpha is the mean of the first group, alpha plus beta is the mean of the second, so beta is the difference between the two. Okay, so the nice thing here is that we can test if there's a difference between the two just by testing whether beta is 0, which is the exact same test that we use to test whether there's a relationship with a continuous variable. Right, so it's exactly the same. No difference at all. We put it into RStudio the same way, okay? So we don't have to do anything special for our categorical variable. So here's the categorical variable sex put into the equation. So this is asking, so we're answering the question, does body weight vary by sex? And we get an overall p-value of 0.48, right? So this is saying that any relationship you see in your data under this model could arise by chance almost half the time, just due to the sampling process, right? So, and this is telling us that actually our model isn't really telling us anything. You can see the multiple R squared is super tiny. We're only explaining 0.1% of the variation in body weight, which makes sense, right? So you'd expect the R squared to be small because the only way that you can explain the variation in body weight is which group are you in? You know, are you a male or female? And of course, within each group, there's going to be a large amount of variation. So we can't explain the variation within group in this model. So, you know, we just have to put up with the variation between groups, which in this case is small. So you can see here that the magnitude of the effect is about 1.7 or 1.8. So this is saying that males are larger than females. So you remember that the intercept here is the average for the first group, right? So in this case, it's females. So females are 121.4 kilos on average. Males then, so the second parameter here is the difference between females and males. So males are about 1.8 kilos larger than females. So the average for the males is about 123.1 kilos. Okay, again, 0.48 p-value. So this number here could well be 0. You can see that again with the standard error, right? So this is the magnitude of the effect, and plus or minus 2 standard errors mean you're definitely including both negative and positive numbers, therefore you're including 0 as a possibility. Okay, so that just summarizes all that, right? So the coefficient labeled sex male is the difference between females and males. Essentially, when you're looking at this and you're trying to figure out you know, what each thing represents, note that you've got a male here, so that must be representing the difference between females and males, therefore the intercept must represent the thing you don't see in the list, females. Okay, we'll see this as we go. Okay, so this difference is not significant, right? P equals 0.48, and that test is in fact exactly the same as doing a t-test for the difference in the mean between two groups, like we did in the first semester. Right? In the first semester we did a t-test for determining is there a difference between two groups. A t-test is just a special example of a linear model. Okay, so here's the same t-test. It's a specific example where we assume the variation in each group is true, but that's just a minor kind of detail, but we get the same result, the exact same p-value, right? So linear models basically cover t-tests. Okay, so that's how you deal with a simple case where you just have two groups. What about where you have three or more? So if we have three groups, then we just extend by adding in more indicator variables. Okay, so if you have three groups, then you have two indicator variables. You have one for the second group. So Z2 and Z3 are our two indicator variables that we're adding. And Z2 we're setting to 1 if you're in the second group, otherwise you're set to 0. Z3 is 1 if you're in the third group, otherwise you're set to 0. Okay. So if you're in the first group, then Z2 is 0 because you're not in the second group, and Z3 is 0 because you're not in the third group. So Z2 equals 0, Z3 equals 0 means that you're in the first group. Okay, if you're in the second group, then Z2 is 1, Z3 is 0. If you're in the third group, then Z2 is 0, Z3 is 1. And you never get the possibility where both Z2 and Z3 are 1, because you can't be in both the second group and third group at the same time. So the linear model is then just the same combination as we'd have before. And you can then see that once again, if you're in the first group, then Z2 will be 0 because you're not in the second group. So the beta 2 times 0 is what you'd have here, which would just vanish, it would go to 0. Similarly, if you're in the first group, you're not in the third group, right? So Z3 would be 0. So you would just be left with the mean of y is equal to alpha. Okay, so alpha again represents the average in the first group, just like it was for when we just had two categories. The average in the second group, well, if you're in the second group, then Z2 is 1, and so you get alpha plus beta 2. But Z3 is 0 because you're not in the third group. So you just get the average in the second group is just alpha plus beta 2. So beta 2 would represent the difference between the first group and the second group. And in the same way, beta 3 represents the difference between the first group and the third group. Right? So the coefficients of the Z's represent the difference from the baseline group to each of the other groups. Okay? So again, we can assess, is the second group different to the first group just by assessing whether beta 2 is 0 or not. And we can assess whether the third group is different to the first group by assessing whether beta 3 is 0 or not. But of course, the primary hypothesis to test here isn't if group 2 is different from group 1, or group 3 is different from group 1, or group 3 is different from group 2. Instead, we want to test, are any of the groups different? Right? So if any of the groups aren't different, if all the groups are the same, then both of the betas have to be 0, right? Because group 2 would be the same as group 1, and group 3 would be the same as group 1, so both of the betas have to be 0. So testing, is there any difference between the groups, regardless of where that difference might be, is the same as testing, are any of the betas non-zero? And that's exactly the same as we had before when we were testing, are any of the numeric variables important in our model? It's just saying, is the model important, which is the F-test, right, or analysis of variance. So an example, here's our, you remember the other data set we're dealing with is the petrels data. Okay, in the petrels data, we collect them across a number of different areas, okay, geographic locations, and we're measuring the right wing length. So one of the things we might want to ask here, and this is one of the things we tried to answer in the first semester, is there any difference in right wing length between the different areas? Okay, and we kind of answered it in the first semester by kind of computing a confidence interval for each group and then seeing whether they overlapped. Okay, but instead, we can actually get a p-value for that directly now from the linear model. So we fit our linear model. Does right wing length vary by area? Same way. We'll get 5 area effects, right? One of them will go into the baseline, in this case area 1, the one that we don't see. And then each of the effects here will be the difference from area 1 to area 2. So this is saying that area 2 is 6 millimeters smaller than area 1 birds on average. Area 1 birds are 389.6. Area 5 birds are 4 units bigger, and so on. And our overall p-value is tiny. You remember your overall p-value is assessing, is something in my model important? The only thing in our model is area, so that's testing, is there a difference between the areas? So our conclusion is very direct here. Yes, there is a difference between the areas. And then the coefficients tell us where those differences lie. So we can see here that area 5 must be the biggest because it's the only one with a with a large positive coefficient. So they would be on average, area 5 birds would be on average 393.7, right? 389.6 plus the 4. Okay, and I guess area 6 birds are probably the smallest, which would be 389.6 minus 9.3. So around about 380.3 millimeters in right wing length. Okay, so those are our conclusions. Overall F-test is what we look at first. That's saying, is anything important? Then the summary table then tells us how they're important. So what are the specific differences between the baseline group and the others? Okay. If we actually wanting to know, so we could actually compute things by hand, right? So if we want to know what the mean is in area 6, right, then we know that in area 6 they're 9.27 millimeters smaller than in area 1, and we know that in area 1 they're 389.6, so you can go 389.6 minus 9.3, do the maths, 380.3, work out what the average is, right? But we have more powerful tools at our disposal, because we actually also know how to do prediction with confidence intervals or prediction intervals, right? So while we can work out the average just using some basic arithmetic, we can't work out what the error around that measure is, right? Because we have to account for the error in the baseline measurement and the error in that difference. We have to combine those errors in some way, and so obviously the computer knows how to do that. We can do that with the predict function, just the same way as we did predictions for the case where we just had body weight versus heart girth. So all we do is we create a new data frame that has the values for the area that we want to predict. So here I'm predicting all areas 1 through 6. And then I just use predict and feed it my new data, and we get our fitted value. So there's the fitted value for area 1, 389.6, which will be exactly the same as we have there. Our prediction for area 6 should be 380.3. There it is there, and so on, right? But we also get our confidence intervals, so we can see our confidence intervals for each of these. Okay, all done all at once. So you can see from the confidence intervals that area 5 is in fact bigger than all of the other areas, because the lowest point is 392.2, and that's higher than all of the uppers of the other 5 categories. So again, area 5 is bigger. We can also visualize those differences with VisReg, okay, which again you'll be looking at in lab 2. So if you run VisReg on your model, then you get this output here. So the output here, because we've got a grouping variable, we've got the areas along the x-axis, the 5 levels, and then your estimate of the mean in each group is the blue horizontal line, and your estimate of the uncertainty is the grey band. And then the dots are just where the observations are, or representations of the observations. Okay, so you can see down in the groups with a very large uncertainty have fewer points, right? So that makes sense. The ones with lots and lots of points have low uncertainty, which again makes sense. And you can easily see now that area 5 is likely bigger on average, because even accounting for the uncertainty, we're above the rest of all of the others. You can see that area 2, 3, 4, and 6 are probably all about the same. Maybe area 1 is between area 5 and the others. Okay. So that's it for lecture 2. Please do attempt lab 2. I will screencast my solutions for that as well later today.